Hello, welcome back to this virtual platform. In today's lesson, I'll be talking to you about circle theorems, and I've divided it into 4 different sections. And in this section, I'll be talking to you about these 3 main theorems, and where possible, go through algebraic proof to support the theorems. Let's start by talking about some of the keywords that you see. So that is a radius, a diameter from one end of the circumference through the center to the other end. That's a diameter. And we have ED is a chord, and a chord is simply a line whose endpoints end at the circumference. So it begins from one end of the circumference to the other one. So you can say BA diameter is also a chord, but it's called the biggest chord, and the special name is called a diameter. And when you have a chord, it divides circle into segments, and a segment is simply a region bounded by a chord and an arc of a circle. So this is the arc EC. This is an arc. An arc is simply part of the circumference. This is the circumference. The perimeter of a circle is the circumference. So the smaller section is called minor segment, and there's another segment here, which is the bigger one. It's called major segment. Then we have a tangent, a straight line that touches just a point on a circle. So it touches BA is a tangent, touches the circle at point C. And the last keyword is a secant, which intersect the circle at 2 different points. So point E and point F. So our first theorem says angle at the center is twice the angle at the circumference. What this means is that whatever this angle is, which is at the circumference, when you double that angle, you get the angle at the center. So if this is x, that should be 2x. In a similar vein, angle B is at the circumference. Whatever the size is, you double it and you get the angle at the center. So if this is y, that is also 2y. Now, to prove why the theorem says so is to go through this algebraic proof. Lines OA, OB, and OD are the radius, as you can see, from the center to part of the circumference is radius, straight line. So that means that we're going to have triangle OBD as isosceles because they have 2 radii, and therefore the base angle here must be equal. So I want to call it x. In a similar vein, you realize that triangle OBA is also isosceles, but the base angle must be the same as well, but the size must not be the same as x, so I'm going to call it y. Now, I'm going to extend the radius to form a diameter to make a straight line, so that we have exterior angles for both triangles. And from our knowledge of triangles, an exterior angle of a triangle is equal to the sum of the opposite interior angle. So the exterior angle here should equal the sum of the 2 interior opposite angles, and x plus x is 2x. So this angle must be equal to 2x. Likewise, the exterior angle here is equal to y plus y, which is 2y. So you can see that angle AOD is the angle at the center and is equal to 2y plus 2x. And if you factor out 2, this is what you have. And you realize that y plus x is really what forms angle at the circumference. So if y plus x is angle at the circumference, then when you double it, you get the angle at the center. Then it clearly proves the point that angle at the center, which is AOD, is equal to twice the size of angle ABD, which is the angle at the circumference. So this is a simple proof. Now pause the video and see if you can use the first theorem to work out the missing angles. Okay, let's start. 45 degrees is the angle at the circumference, so the center angle should be double 45. You have 90. Also 75 is angle at the circumference. We double 75 to get A. That gives us 150. This time we have angle at the center, so you got to reverse the rule. So we got to divide 290 by 2 to get the angle at the circumference. So that's 145. This is also similar. Don't get confused. The diameter lies on top of a radius, so that's why you can only see one line here. So this is still regarded as angle at the center. So double 30, you have 60. Now take note over here. Angle A, the center angle that it makes reference to is this side, not the 80. So the A make reference to this angle. To work this out, remember angle at the center around a point is equal to 360. So we need to compute that first. So that's 280. Therefore, we can now have 280 and A will be 140 degrees. So that's theorem 1. Second one says angles in the same segment are equal. Angles in the same segment or angle from the same arc and in the same segment must be equal. So this is what it means. So you can say that, like I said, segment, if you have a chord that's BC, we have a segment at the bottom and a segment at the top. And these two angles are in the segment at the top. So which means they are found in the same segment and they must be equal. That's what the theorem says. Now let's see why it is so. Let's see the proof behind that. So we're going to prove that A is equal to B. Now recall from theorem 1 that says that angle at the center is twice the angle at the circumference. So I'm going to create an arbitrary center angle. I'm going to call it X. And you know A relates to X in the same way as B relates to X. So you know that X must be equal to 2A because the center angle is twice the circumference angle. In the same manner, X must also be equal to 2B. And since X is common to both, we can say 2A is also equals to 2B. So if you divide through by 2 or cancel out the 2, you end up with A equals B. That is what the theorem is saying. So in short, you realize that A and B, which is angles at the circumference, have the same relationship with angle X, which is the angle at the center. Okay, now pause the video and see if you can use angles in the same arc or in the same segment being equal to work out the missing angles. Okay, let's check it. So you can see A and D are in the same segment. This segment called BC is the chord or BC is the arc. They both stand on the same arc and they are in the segment at the top here. So they must be equal. So X is 85. Now 65, now AD becomes the chord now. And having AD as a chord, the segment left is this section and B and C are in the same segment. So Y must also be 65. Now when you come to this point, you realize that you know angle A and D are in the same segment, so they must be equal. But you don't know either of it. So you need to find out D to be able to relate it to X. Now here, you don't have to lose your facts about angles. Remember that OD is radius, OC is radius. That makes ODC isosceles, and therefore the base angles must be equal. So 65 degrees, that means that's also 65 degrees. Now knowing 65 degrees for D, then A and D in the same segment, then X must also be 65 degrees. Okay, the last theorem we're going to prove in lesson 1 is the third one, which says the angle in the semicircle is 90 degrees. What this means is that if you have a triangle that fits perfectly inside half of a circle, then this section must always be 90 degrees. The angle at the circumference must always be 90 degrees. In the same way, in this green triangle, you realize that this section must also be 90 degrees. Let's prove that also. We can start by looking at these two triangles. That is isosceles, and that is also isosceles. So, similar to what we did in theorem 1. So that's A and that is A. That is B and that is B. And you know each triangle add up to 180. So knowing A and A in one of the triangle, the last angle should be 90 minus 2A. So 180 minus 2A, because they all add up to 180. And the second one, the missing angle must also be 180 minus 2B. And you realize that BC is a diameter. And diameter is a straight line. And angles on a straight line make 180. Therefore, when you add these two up, 180 minus 2A plus 180 minus 2B should equal 180. And if you work it out, you end up having 180 equals 2A plus 2B. Factor out 2A on the right hand side. Factor out 2 on the right hand side. You end up having 180 equals 2 into bracket A plus B. So I'm going to divide through by 2. And now what I have is A plus B. And where is A plus B? A plus B is the angle at this corner. And that is why we say that must always be equal to 90 degrees. This is similar to the first theorem because after all, you realize that BC is a straight line. And angle at the center is what? 180. And therefore, angle at the circumference should be half of 180, which is also 90. So whichever way you approach it, the rule still works that this corner must be 90 degrees. Now pause the video and look at these questions and see if you can find out the missing angles. Okay, let's check. Right. X, we know that it's a triangle. It fits perfectly into the circle and fits half of it because that is the diameter. Therefore, this must be 90 degrees. In the same way, angle C, this is diameter, so it's half of the circle. So therefore, this must also be 90. Another way of knowing it's 90 is that they both in the same what? Segment. Remember, BD is also a chord. It's the longest chord in the circle. And therefore, in this segment, all angles at the circumference should be equal. To find out X, you need to remember in triangle DAB, we already have 35. But you know this corner is 90. And angles in triangles add up to 180. So knowing this as 90, 35 plus a number must be equal to 90. So 35 from 90, that gives you 65. Now to find out why the same way, you know this corner is 90 and this is already 70, but 70 and y must add up to 90, so this one must also be 20. So that brings us to the end of lesson 1, and I hope you've enjoyed it. Please share with your friends and look forward to lesson 2, where we continue with the theorems 4, 5, 6 and 7. Thank you very much for watching.